Welcome to Objective 6.6. This is where we get to do some math with the magnetic declinations. So I'm just going to walk you through the steps first, and then I'll give you an example, and then we're going to work through a couple more examples as we go. And then we're going to add in like an azimuth or bearing, and then go from there. So, magnetic declination calculations. What is this? So this is how we get from each north to the next one. The thing is, again, the magnetic north is always changing, so therefore we need to keep in mind the time from when the map was published to when you're actually looking and doing the calculation. So this is really important when you go forward with these calculations. So first of all, you calculate the time that has been between that it has been between the year of the map and the year you were looking at. So if your map was created in 2007 and it is now 2020, you're going to have 13 years. Then what you're going to do is you're going to look at your map, and there's a little diagram that will show you, and I'll show you an example here in the next slide. And you're going to find the rate of change, and you're going to multiply it by that many years. So that's going to give you the total amount of change. I do suggest number 3 is converting it from converting that value to DMS. Again, it's just merely easier to work with rather than working with some of the strange decimals that you end up working with. That's just my suggestion, though. Also, you can go about those first 2 steps as you please. If you don't like the way that I'm referring to it here, you can approach it another way. Then step 4, I suggest calculating the original magnetic declination. That means figure out what is the declination, the magnetic declination to be specific, from the true north to the magnetic north. Each map actually doesn't say that. It only gives you the convergence angle and the grid declination. So keep that in mind as you are working through your questions that you're not given that. And that's why I include this step. And then the last is that you're going to add or subtract the change from the answer you got from 4. So this is to adapt for that change, right? So you calculate the change up here, and then you take the original magnetic declination and apply that change. Sounds simple enough. Maybe I'm making it more complicated than what it really needs to be in 5 steps, but it's just helping break it down for those of you who need it. So here is an example. So here is the little diagram you're going to find on your maps. You're going to find this on your NTS sheets. Anything that's a topographic map, you're going to see this. So you can see the little symbols that I was mentioning before. So we have the true north with the star, the grid north with the little square on the top, and the magnetic north with a little arrow. So we see here that we have from true north to grid north. That's my convergence angle. It tells me that it is 1 degree 55 minutes. Okay, so that's what this is. This does not change. Okay, so it never changes, so therefore it always stays the same. So that's a nice standard one. Then it tells us from the grid north to the magnetic north, it is 13 degrees 41 minutes. That means from the grid north to the magnetic north is that value. It is not from the true north. So we have to actually figure that out when we do the original magnetic declination. Then down below, it says this is the approximate mean declination in 1999 for the center of the map. Okay, so obviously as you move around your map, you're going to see different things, and that's okay. That's that declination is going to be a little bit different every time you move around. And then it says an annual change increasing by 2.4 minutes. Now, we say do not ever use minutes, or minutes. Don't ever use decimals in your minutes. So make sure that's kind of a funny thing here, but the reason that they leave it as that version is because it's easier to do the math when you're working with larger dates, right? Because we're looking now at like being 2020. We're looking now that this is 21 years ago that this was done. So we go back up here. It says, what is the magnetic declination for 2020, which is the year that we are in at the moment? So 2020 minus 1999, it gives us 21 years. Then we take 21 years and we multiply it by that 2.4 minutes. That's not feet, it's minutes. So 2.4 minutes, and that gives us 50.4 minutes. So now, as I mentioned in my previous slide, that step 3 converted into DMS because zero point 0.4 minutes is really hard to conceptualize. So we switch it into 50 minutes and 24 seconds. Then we have 13 degrees, 41 minutes, which is my magnetic declination, and I minus 155 because that is my convergence angle. And then we get 11 degrees 46 minutes, right? So can you see why we do that? We have the angle all the way across from the grid to the magnetic, and then we have the angle from the grid to the true north. So all we need to do is remove this portion, and then we can calculate what's in here. So that is the original magnetic declination. Now we have to figure out the actual new location of the magnetic north, which will be out here. So it is increasing, and so therefore it's going to be moving out, and therefore we need to add it. So we take this original magnetic declination, we add the change that we calculated in 3, and then we get our answer of 12 degrees 36 minutes 24 seconds. Okay, so that is the declination examples. Now I'm going to work through a next example with using azimuths, and then we will I'm going to do a few more on my little whiteboard. Okay, so here we are. We're just going to use the same diagram, and it's easy to use. So you guys have figured out the magnetic declination information already. So here we have town A located at these coordinates, and town B is located at those coordinates. What is the magnetic bearing going from town A to B in 2015? So as soon as we see coordinates like this, they are grid north, always based on grid north. Longitude and latitude would be based on true north. But if you see anything with meters, it is immediately grid north, because meters makes a grid. Okay, so really caution, I'm going to caution you on that. So let's go to the how we work this out. So first of all, I want to figure out what my grid azimuth is from A to B. So to figure out my angle, I have my tan -1 with the delta x over delta y. So I take my final position and I make it into the final position into the first starting position, and I do the same with the y, and I end up getting -87.1835. Now, knowing that this value, it goes down in the x, and it is going up down in the y, is it? Or up in the y? 618, 612. So this one actually goes up in the y, so that means that it is going to be in the northwest quadrant. It's going to be in the northwest quadrant. So in order to get this to be a positive, I would add 360. Now I'm saying add 360 here. What it actually is I go 360 plus -87, and that gives me the 272 degrees, 11 minutes and 11 seconds. Okay, so that's how I get that. So I go from here to here doing that. And I have to check this because if it was -87, it could have been in the southeast quadrant, right? So we have to watch that. Okay, so magnetic declination. So here we've got the whole process which we did. So except the difference is this time we're doing the 2015 rather than 2020. So we have 16 years. We take the 2.4 minutes and multiply that by the 16 years. Then we convert that into DMS. And then the original declination, which doesn't change from the previous example. And then we said it's increasing because it's just said that in the diagram. So we add that and we ended up with 12 degrees, 24 minutes, 24 seconds. So this is just the diagram, right? So this is where my magnetic north is located with respect to my true north. Now we're going to determine the new grid declination. Okay, so the grid declination was 13 degrees 41 minutes, and then I'm going to actually add 38 minutes 24 seconds to this because I am trying to go from grid north to the magnetic north, and I get 14 degrees 19 minutes 24 seconds. This is the angle between the magnetic north in 2015 and the grid north. Okay, so now we know where the magnetic north is with respect to all the norths. We know all the angles, so now we can work out where what north we need to get to. So it says now we need to determine the angle between the vector of town A to B and the magnetic north. So here we have 272.11 minutes 11 seconds that we determined. That's what the grid azimuth is for AB. Then we know that the magnetic north had moved, and we calculated the new grid declination. And we know that the magnetic north moved away, and that the way that the diagram is set up, that we actually need to add. So we're going to add that, and we end up with 286.30 minutes 35 seconds. And then we need to calculate the bearing. So we're going to take 360 minus that, and we know that it's in the north quadrant. It's 73 degrees 29 minutes 25 seconds from the north line and west. Okay, so this is my bearing. So that is a really quick example of how to do this. I am going to also show you guys how to do this on the whiteboard here. So let me just end the slideshow, and I'm going to do this and remove that. And here we go. All right, so in our examples, we have been dealing with these diagrams. And so this is probably the hardest conceptual objective that we have, is trying to figure out what is going on in this case. So I'm going to use a whole bunch of colors for this again, because it just makes way more sense to do it this way. So let's use green for my north, my true north. So here's my true north. Okay, there's my star. And then my magnetic north, I'm going to use red. So let's put the magnetic north on this side for a little bit of change. And in fact, in Calgary, that's where it should be sitting. And then we're going to have grid north, which why don't we put it on this side instead? It's kind of big. That's a big angle. Maybe I'll make it a little bit less of an angle. There, that's a little better. Okay, so there's my north. This is the orientation that they're at. So if I put in, I'm going to use a little pencil color. So going from true north, not true north, because I wouldn't give that to you, grid north all the way over to the magnetic north. Let's say that is 10 degrees 31 minutes, and we'll just leave it at that. Okay, so that's what that one is. This. Then the angle between the true north and the grid north is the convergence angle. And let's say that one is 2 degrees 32 minutes. Okay. And so that's what would be given there. And then we're going to use black. And here we're going to say that the starting in, let's say 2001. So this is when this map was created, is in 2001. It is decreasing. I'm going to add some fun here. So we're going to decrease by 14.4 minutes per year. Okay. So now, what is the magnetic declination for 2020? Okay. So that's the case. Let's go. All we're doing in this case, in this example, is trying to figure out what is the magnetic declination. So this one says it's decreasing. So that means that my magnetic north is actually now going to be, my new one, is going to be in here somewhere, right? So that means this angle between the true north and the magnetic north is actually going to get smaller. So our goal is to figure out how that is, so, or what that value is. So step one in the magnetic declination formula is figuring out the year difference. So we go to 2020 minus 2001, and this equals 19 years. Right? So that's step one. Step two is trying to figure out the change. So it says 14.4 minutes. So we're going to say 19 years times 14.4 minutes, and use quick calculation with that. I get 273.6. So 273.6 minutes. Now, can I have 273 minutes? No, I can't. So I'm going to separate this up. So for those of you who haven't seen this before, how often or how many 60s can go into 270? So we're going to do, oops. So I'll give you a chance to think about that. And so 6 times 4 is 24. 6 times 5 is 30, so it goes into it 4 times. So step 3, 273.6. If we say divide by 60, that gives me 4 degrees, okay, and remainder. So at 4 degrees, we have 273.6 minus 240, right? Because that's how many degrees I'm taking out. Or not degrees, but minutes I'm going to be taking out to make it into degrees. So that's going to leave me with 33.6 minutes. So 33 can stay the same. So I can say 33 minutes because that's not above the above 60. And then I'm going to take the 0.6 that's remaining. I'm going to multiply that by 60, and that gives me 36. So now I know that my change is 4 degrees, 33 minutes, and 36 seconds. Okay, so this is the change. That is how much this in here has moved. Okay, so that's the calculation that we just did. Then for step 4, we figure out the original magnetic declination. So I have 10 degrees. I take my grid declination, 31 minutes, and I'm going to minus the 2 degrees, 32 minutes. And that gives me, working backwards of that, 7 degrees and 59 minutes. Double check my math there. In the classroom, I make you guys do this work, so you gotta check it out, make sure it's correct, and go from there. Okay. So with that, now we have, and if you don't know how I got this 59, let's just do it this way. So 10, 31, and then we have 2, 32. So this has to go down to 9, and this becomes 91. Okay, so maybe I am incorrect. Oh no, I'm right. So 91 minus 32, go 8, 11, so that's 9, and that's 5. There we go, so I was correct. Okay, so that's how I got 7 degrees 59 minutes from that. Okay, so then the last step is trying to find out what is the actual declination going in here. So we're going to subtract this time. So I'm going to take my original declination, which I just calculated here, which was 7 degrees, 59 minutes. Okay, so that's the original declination. And then I'm going to subtract this, because what I calculated here in 3 is this angle in here. And subtract 4 degrees, 33 minutes and 36 seconds. And let's do the math on the side here so you can see how to do it in your head if you want to. Okay, so this is all zeros here. So I take away 1 from here. I have 58. And this is 60. And 36, so that'd be 24, 25, and 3. So my answer for my new magnetic declination is 3 degrees, 25 minutes, and 24 seconds. So I'll leave that up there for you to kind of think about and consider. So I'm going to go back. I'm going to draw a new idea as to what you could see, because there's all different ways to place these and add values and everything else. What if we mixed up the norths like this? So go in here, my purple. So I'm going to use the same locations for the colors just so that you can visually see the different colors. So my convergence angle from my true north to my grid north, let's say that is 1 degree 57 minutes. Okay, so that's that one. And then I got not orange, black. Then my original grid declination goes from grid north to magnetic north. And let's say that is 2 degrees 10 minutes. Okay. Then we're going to say that in 2005 it was increasing at 11.9 seconds per year. So what is the magnetic declination in 2020? So first step, we figure out the date difference, right? 2020 minus 2005, that equals 15. Easy first step. Second step, I need to figure out the total change. So I'm going to take 11.9 and I am going to multiply that by 15 years. And that gives me 178.5. Okay. Then we're going to adjust this. So 18 would be 3, so 180 would be 3. So it doesn't quite do 3, so we know it's 2 degrees. And then I'm going to have, let's do the math over here. So 178.5 minus 120, because that's 2 times 60. So that's going to give me 58.5. So I'm going to have 58 and 30. Right? So you can see how, I hope you can see how I did the math there. Really, I'm just taking this, I am making 178 into degrees, so I'm figuring out how many degrees that is, and then I'm taking this 0.5 and making it into seconds with the remainder there. So that's step 3. Step 4 is figuring out the original magnetic declination. So this example is different. This is why these placements of these angles is very, very important, and you have to draw it out. Please draw it out. If I give it all to you in words, you need to draw it out to try to figure out where they're located, because otherwise it becomes really confusing. I can't even do it without trying to draw it out myself. So the original magnetic declination, I have to add the two. I'm not subtracting this time, I'm adding. So I have 1 degree, 57 minutes, plus 2 degrees and 10 minutes. So this equals my, let's see, 4 degrees and 7 minutes. Okay. So that's the original magnetic declination. This number 4, let's go to the original I had as, I didn't draw it in there. I'm like, what? Why is it I don't see the other color in there? So we'll use brown. So now we have this full value here. Okay, so from the true north to the magnetic north. That is what this is in 2005. So then 5, and now we're going to try to figure out this value and this value need to come together somehow. It says that it is increasing, so that means that my angle has gotten bigger, so that means it's coming out. So we're trying to figure out the angle from true north to this new dotted flag. So this 4 is this brown. This 2 degrees is in here. I am going to have to add the 2 to make it into that value. So we have 2 degrees, whoops, sorry. 2 degrees, 58 minutes, 30 seconds, plus 4 degrees, 7 minutes. So that will be 30 seconds, 5 minutes, and 7 degrees. And that is my magnetic declination for this example. So as you can see, you really have to watch a couple things in the question. You need to know whether it's increasing or decreasing, and you need to know the placement. What makes increasing and decreasing really confusing is when you put it on the flip side of true north. Erase those. And I do an example here, so actually write this here. And we'll erase this. Okay. Line down, and we'll do one more example, and hope it helps you set these up as we go. So if we put my true north on this side this time, true north, then we put magnetic north on this side, and we put the magnetic north right in the center. So flipping everything around. Again, check the diagram. Make sure you see the diagram and you understand the diagram, because if you don't, you're probably going to end up getting lost with your calculation. So my convergence angle goes from true north to the grid north. So it goes like that. And let's say this one is 16 degrees, 46 minutes, and that should be good. Then we know that the grid declination, which is, it goes from grid north to magnetic north, like that. This one is going to be 3 degrees, 17 minutes. So that's what's given to you. This, you will also know the year. So this was originally done in 2008. And we found out that it is decreasing by 12.3 minutes per year. And then we're trying to figure out the magnetic declination for 2020. So let's find out the years. 2020 minus 2008. And then we get an answer of 12. We're going to figure out the total change. So 12 times 12.3. And that gives us 147.6. Then we're going to do the math with that. So we know there's going to be 2 degrees, it's going to be 27 minutes, and 36 seconds. So that's the conversion of 147.6 to that. And then step 4 is trying to figure out the original declination. So we need to find out the value in here. So we have 16 degrees, 46 minutes, minus 3 degrees, 17 minutes. And that is 13, 12, and let's see, if it was 20, it's 29. Okay, it's 12 degrees, 29 minutes. That's the original declination in 2008. Now we need to apply this. It says that it's decreasing. What does it mean by decreasing? It means that it is going closer to the true north. So this is where this is going to be. This is decreasing. This is where people get really confused because they're like, what? Well, but over here, if it's decreasing, it's going the other way. It was actually going, counterclockwise. And this time is now going clockwise. When it says it is decreasing, it means it is becoming smaller and going towards the true north. That is what it means. So now knowing that, so now we know that this original declination, which is in brown, so the original declination goes from here to here, okay? So that is this value. Now I need to decrease it. So I need to figure out the value in here, okay? So step 5 is we're going to take this actually the 12 degrees, because we're going to start with the larger number. 12 degrees, 29 minutes. Now it says it's decreasing, and let's look at the diagram. So the brown that we had calculated is to there. We have, let's choose this one. We have this value in here, which is this 2 degrees. Okay, so let's just do a little legend here, 2 degrees here. So we need to figure out how to go from here to just this. So we're going to take this value, which is the 12 degrees, 29 minutes, and we're going to subtract my little teal color here. So I'm going to subtract 2 degrees, 27 minutes, 36 seconds. And that gets me, I'm going to do this the long way so you can see it. Okay, so this is 28, this is 60, 5, 10, 4, 24, 28 minus 27 is 1, and then 10. So my answer is 10 degrees, 01 minutes, 24 seconds. All right, so that is how we do the magnetic declination. Now, if we add, I'm going to just save this for you guys, and we can put it into File, and then it's saved. You can see my directories all set out here. So I'm going to put this in here. I'm going to call this magnetic declination. Hit save. And we got that one. All right. So it's saved. Let's close that. Now we can do the next one, which is going to be adding in a line. So I have town A, which is here. I have town B, which is here. They have a line between them. There is my magnetic north and true north diagram, which is over here. I'm just going to kind of go with the standard one here for a moment. We have the magnetic declination there, and we have grid declination, which is over here. That grid declination doesn't want to go straight very well. So we have town A to B. This is going to be based on grid north, right? So this is grid north. Because I'm going to give you coordinates for A to B in grid north, so it is always based on that. My suggestion is to take this diagram and sketch it out for yourself wherever you are starting. So we're going to go here, and then we're going to draw it over here. Okay. So with this, I'm going to give you guys the values in here. So in here, we have 6 degrees, 11 minutes. And then we have our other one, which is set up, which I can't remember what color I was using. Let's just use bright green. From here to here, not at there. We're going to go all the way to here. So the grid declination is going to be, let's say, 16 degrees, 1 minute. Okay, so we have those. Now we have to have the year that this was. So in 2007, it is increasing by 2.9 minutes per year. Okay. So the AB for the grid north, that angle is going to be 97 degrees, 15 minutes, and 20 seconds. Okay, so that's my angle. I know that does not look like 97. Maybe I should do that so that it looks like 97. Or not 97, but make it look like a value that it is closer. So let's say it is 81 degrees and 15 minutes and 20 seconds. There we go. So now we're working in the right quadrant, so it makes it a little bit easier for an example. So going from there, we are going to determine, first thing first, I want to determine my AB. So that's already been given, so I don't need to calculate that with the coordinates. So I'm lucky there. So the next thing I want to do, so I'm going to say not my magnetic declination. I want to find out what the magnetic azimuth of AB. So the magnetic azimuth of AB means I need to go from the magnetic north. So in 2020, So we can see that there is going to be a fairly significant gap. So this is why we need to do the magnetic declination, because what happens is this changes. This is going to go like that, right? Because it's increasing. So that means this is going to go like that. So that means the angles that I am dealing with in here is I have this one originally, right? And then I need to figure out this one. So I have lots of angles that I got to deal with here. So this is why drawing it out is so incredibly important. All right, so we've got the value. We already have the angle, so we're good there. We don't need to add any more. So the first thing we need to do is determine the magnetic declination for 2020. So the first step in magnetic declination is to find out the year difference. So we have 2020 minus 2007, and that equals 13 years. The second step is find out the change. So I have 2.9 times 13, and that gives me 37.7 minutes. Third step is to put this into something proper. So I have 37 minutes, and 0.7 would be 42 seconds. Okay. So there's the first three steps. So that tells me the change. So that is the difference between where the orange flag is, or the orange magnetic north, to the red one. Then do we need to figure out the magnetic declination, the original one? That's up to you. So some people may say, well, I don't need to determine it, so I'm not going to. That's fine. You don't have to if you don't want to. I am going to do it because I want to keep and maintain the same flow as we go all the way through the instructions, and it's good practice. So if you think you've got this down, then you don't need to do this, but if you need the practice, then I suggest keep doing it. It's not going to eat up that much time for you. So my original declination is trying to figure out this angle in here. So I take 1601 and I subtract 611. No, just one. There's only one of those. So that should be, let's see, 10, 9 degrees and 50 minutes. So that is my original declination. So that is from here to here. Now we need to find going from here all the way over. So 5 is I need to add that change. So I have 9 degrees, 50 minutes, plus the change, which was 37 minutes, 42 seconds. So that gives me 10 degrees, 27 minutes, and 42 seconds. Okay, so now I have this angle in here. But I'm looking for the magnetic azimuth of AB in 2020. So I need to go to this flag here, which means I need to have the angle, I won't use dark green. I need to have the angle from grid north all the way over to this. So I need this angle in here to make this difference. So how do I do that? What angles do I have and what don't I have? Really, all I need, I have the 16 degrees 01 minutes plus this little bit here, right? That's all I need. So to get my grid declination, I'm going to say 16 degrees 01 minutes, and then I'm going to add the difference. So I have 37 minutes 42 seconds, and that's going to give me 42 seconds, 37, 38 minutes, and 16 degrees. So that's going from here to the grid declination. Now I need to find out where this blue is. So I have this, and I have this purple. So I have this one here, and I have this one here. So to get this part, I need to take the grid azimuth that I have been given, and I need to subtract the magnetic or the grid declination. Not the magnetic one, but the grid. So I have 81 degrees, 15 minutes, 20 seconds. Subtract 16 degrees, 38 minutes, 42 seconds. And that is going to give me, and I'm going to do the long hand over here. Again, just so that you can see what I am doing and how I work with this. So I'm going to need 14, 80, 7, 10, that's 8, 3, and then I need to take away 1 from here, so we're at 80, 74, 6, 14, 6, and then 80 minus 16, 4, 64. So my magnetic azimuth is now 64 degrees, 36 minutes, and 38 seconds. Okay. So there's lots of math in here. I do this as an extra step, or even like both of these as an extra step in there. If you find it easier not to follow the full worked out formula and trying to put that into the diagram and trying to figure out what's what, if you are having too much trouble with this part, when you are given this, you can definitely work it out in another way. So you have the other example on the PowerPoint slide of how to do it with coordinates. Just making sure you watch these angles and how they are pointed with respect to each of these true norths and what direction this is moving. So you can see that it is really important here that when I say I increase by 2.9 or 2.9 minutes, I'm watching it go away from the true north, but it is moving closer to this grid line, which means that this is actually subtracting that difference off. So you have to be really careful. Please draw it out. It's going to help you see what's going on. I can't emphasize that enough. Draw it out, draw it out, draw it out, draw it out. Take your time to draw it out because it's going to help you. So this is probably the hardest concept that you could possibly work with in this class. Don't worry, it's not going to make or break you. If you really don't get it, it may eventually come to you. The reason, again, why do we do this? You get out into the field, you're dealing with a map and a GPS. Map is the grid. The true north is your GPS. GPS doesn't work in the forest canopy, so now you've lost your true north. All you have is your grid, which really doesn't give you any real world other than some visualization if you're walking along a stream or something. So if you're in the middle of a bush, you really have no idea. So you pull out your magnetic compass. Now you have to figure out, using your map, taking this and following the direction from the magnetic north. You do need to know what year you are in because this changes. And in fact, it can change quite a bit. Right now, the magnetic declination in Alberta is, or in Calgary, is about, I think it's like 17 or 18 degrees. So it's quite a large value, and it has changed over a degree in the last little bit. So it is still important to know because you still need to work through that. But that is magnetic declinations. So please take your time with your assignments. I have the activities there for you to work with to try to work it out. And I will see if I can make a few more examples for you to work through and with some answers for you. Okay? All right, we'll be moving into Objective 6.7 next.